concentration determination. And there's two versions of the problem. The easy one, we're going to learn three things pretty quickly. We're going to learn the two types of problems. We'll also learn the difference between a chemist and an engineer.
Oh, shit.
Nice.
Chemists are good at numbers. Engineers are better. Chemists are lazy and look for a way around the hard math to find the quicker way home. And you'll see that.
You call this easy?
What's that?
You call this easy?
Oh, no. I'm going to show you a trick that when it applies, it makes life easier. And I'll show you how to find it. Once you see it, when you start your equilibrium problems, you start working on them, you automatically look for this idea. If you can pull this one off, you slide by the math real fast. You simplify. And it, numerically, if you miss it and you do all the math, it doesn't matter. You get the same number. If you can get home a little quicker, it's a good thing. First type of problem. You have K and all the concentrations at equilibrium are known except for one. That's one type of equilibrium problem. Example 4.8 has that. They gave us an expression. They said that I2 breaks down into two I's. It has a value for its Kc. It says we know at equilibrium I2 is 0.1 molar. We want to know what's the concentration of the other species at equilibrium. This is the easier type of problem because all we need to do is write an equilibrium expression and sub in and solve for what's missing. So equilibrium expression for this reaction says that Kc equals 0.011, which equals concentration of I squared over concentration of I2. Well, they tell us what I2 is, they just don't tell us what I is. So all we have to do is now write this expression with what we know. Concentration of I is what we're looking for. Concentration of I2, 0.10. We can solve that pretty quickly for I2. Multiply, take the square root. And when you do that, we'll get that I equals 3.3, 10 to the minus second. Concentrations are all in moles per liter, so you can carry that right through. And you have the answer. Nothing more, nothing less. You'll have what's missing. So to solve for this, remember, we're going to take this, multiply it by this. You need to take the square root to get rid of that. This is the concentration again. That's one type of equilibrium. K was known. We knew all the concentrations except for one of them. We solved for the missing variable once you write your equilibrium expression. That's the one that takes the least amount of time. The second type of problem, and this one's going to come, actually came from a different source. Let's take a look at this problem. In order to do this one, I'm going to clear off what we just did, so I'm going to need a little room to solve it. So I'm going to clear this one off and then write the next one. This one says,
That's the whole problem.
they tell us that we have a reaction, balanced chemical reaction. We have an equilibrium constant Kp, and they tell us at the initial point, initially, we have 4 atmospheres of H2 and Cl2. That's our starting amount. Starting amount, not at equilibrium, what we're starting with. They ask us to find the equilibrium concentrations of all species. They tell us where we're starting. They tell us nothing about where we end. They want us to know, find it all out. The procedure that you'll go through for this problem follows the same step. First thing we have to do, we have to write an equilibrium constant expression. Kp in this case equals products over reactants. HCl squared, H2, CO2. That's what it equals. Next thing we have to do is we need to put together an ice table. So we need to track products and reactants. So let's put our ice table together. Initial change. H2 plus CO2 Now we have to look at, what do we know? We don't know much. That's what these problems become pretty evident. You know, there's not a lot we know about what's going on. We know the initial concentrations of the two gases, H2 and Cl2, are 4 atmospheres. We can assume that when the reaction started, none of the hydrochloric acid was present. Assuming that no product was present before the reaction started. So we'll put a 0 in this bracket. And that's where it ends. There's nothing else that they've told us. They want us to know what happens at equilibrium, what the concentrations are. What we do next is we look at the change. We look at the coefficients that we have, and we look at what would the change be. We have to do it in terms of a variable x.
So pretty much no matter what the problem is, if they don't give you an initial for the product, it's going to be 0.
Yes, unless they say a certain amount is present, assume it to be 0, right? Absolutely. Right. So if we look at this, it's 1 to 1 to 2 for the stoichiometry. So whatever we would lose if we called x for this guy, we would lose the same amount of the other one. Just because you lose x amount of one, x amount of the other. It's negative because it's on the reactant side. It's what we're losing. Now, product side, we're gaining, but the ratio says we're gaining 2 for 1. So on this side, positive, and it's 2 of whatever x is. So if we look at what do we know in equilibrium, we just do the column. This is 4 minus x. This one is 4 minus x. This one is 2x. That's all we know. We don't know what x is yet. If we knew what the numbers were, we would put it right back in the equilibrium expression. And we can. We're going to do it with the x. Taking our equilibrium constant, which they say is 0.45 equals Kp equals the HCl concentration squared. HCl concentration there is 2x. 2x, quantity now squared. On the bottom. Both of our individual concentrations. 4 minus x times 4 minus x. What we have here is what's going to be a quadratic expression when it's all said and done. We're going to get an x squared term, an x term, constant. It's a quadratic expression. The chemistry ended now. Now it's the math to find x. First thing we do, let's simplify things a little bit. And let's take a look at this denominator.
16.
If you remember, foil, first outer, there's last. We thought that was dead years ago. We might as well take care of the top. 2x squared is 4x squared. So we'll take care of the top, 4x squared. On the bottom, it's correct. 16 minus 4x plus x squared
So it's just 16 minus 8x
Yep. Yep.
plus x.
Now, what we're going to do is we have to get this in the standard form. We have to get it in a form where we have the x squared term, the x term, and the constant equals 0. That's going to be the work, to get it in that form so we apply the quadratic expression. To do that, I can take this whole denominator here, 16 minus 8x squared equals 4x squared. All I did was swing the whole thing up, added the two 4x's together, and brought it up so that it's now one side versus the other. When I multiply this through, I take the 0.45 and I walk it through the terms. 0.45 times 16, 7.2. 0.45 times minus 8 becomes minus 3.6x. 0.45 times positive x squared becomes positive 0.45 x squared, or x squared. To get it in the standard form, the easiest way to do that is I'm going to swing everything over. I'm going to make it, keep the 4x where it is and move everything to the other side. It doesn't matter which way you go back and forth with it. Either way it'll work. I just like to have a positive x squared term. Let me show you what happens when we do that. Moving everything from this side to this side. So when we look at what happens there, we get 4x squared stays on the one side. I'm moving over the 0.45, so I'm taking away 0.45 x squared. I'm moving over to the 3.6, so I'm adding 3.6 x, taking away 7.2, 0. The only thing I have left is I have to add these two terms together. 4 minus a 0.45 would be 3.55. Squared. Now I have it in a form. I have the x term, the x squared term, the x term, and the constant, all mine, and I can solve that. The way that we solve that is the use of the quadratic formula. X equals negative b plus or minus the square root b squared minus 4ac 2a. A quadratic expression gives you two answers every time.
Yeah.
Plus,
We only need one of them. Only one is a unique solution to the problem. We'll sort out when the answers come out which one's right. Be careful when you've gotten this far that your terms, I usually write underneath, this is the constant A. This is what A is worth. This is what B is worth. Be careful when you get to C. C is minus 7.2. Forgetting the minus there blows the whole thing up when you try that, because it will throw off what's underneath the radical sign. So we plug in to this expression the values we have here. Negative of b. Well, b is 3.6. Negative 3.6 plus or minus square root b squared 6 squared minus 4 times a 3.55 times c. This is where it will. If you forget that minus there, this whole thing here will become more negative than the front part, and you'll get a negative underneath the square root or something like that. 2 times a, 2 times 3.55. If I start to collapse everything underneath, let me show you the next part. 6 plus minus. 3.6 squared is